The evolution of a star is kind of complicated. The book really glosses over it. I'm going to try to explain it to you, hopefully in a way that'll be a little easier to understand. Okay? It's a step-by-step process. Remember that a star is a happy, healthy adult star, as long as it's converting hydrogen to helium in its core. That's when it's on the main sequence in the HR diagram. And remember that the star will eventually run out of hydrogen in its core, and that's when it begins to die. So, I have here a model of a star. Here's the core. This is where the magic happens. This is where the hydrogen is converted into helium. That's the rest of the star. Nothing's going on there. There's not enough pressure to slam those protons together and fuse them. So no fusion, fusion. Okay? Nothing happens. The magic happens. When is the star going to die? When all of the hydrogen in the core has been converted into helium. When all of the hydrogen in the core is converted into helium, there's no more fusion in the core. Because there's no more fusion in the core will begin to collapse under gravity. Because nothing can counteract gravity at that point, right? There's no energy being created, so there's nothing to stop gravity from pulling the core in. So as the core gets pulled in, it gets hotter and hotter and hotter. And that heat travels outward from the core. Now, remember all this hydrogen out here that couldn't do anything? Now it can do something. Because all of the heat, which is escaping from that helium core that's collapsing in on itself, makes a ring of hydrogen out here finally get hot enough to fuse. So you start getting fusion, not in the core, but in a shell surrounding that core. And this is something that we call shell burning. It's a really bad term. Okay? It's not really burning like a fire, it's fusion. So hydrogen is now converted into helium, not in the core. The core is just a glob of helium that's collapsing, but it's occurring here. That's not normal. That's not right. That's not stable. And so what happens is that the outer layers of the star actually get pushed out into space. So the star actually begins to expand. It gets very large. And as the outer part of the star gets further away from that heat source, the outer layers cool off and turn red. What kind of star is big and red? I know, a red giant. That's right. So that's when our sun's going to become a red giant. After it's exhausted all the hydrogen in the core is turned into a glob of helium. The helium is contracting under gravity and heating up. That heat then causes a ring of hydrogen to helium fusion in a shell around the core. The star becomes very unhappy, unstable situation. Outer layers move out into space. All right, here's where magic is part 2, but it's actually a cheating kind of magic. Remember this core of helium that's collapsing under gravity and heating up? Eventually, it gets hot enough that it begins to fuse. And what happens is that the helium fuses to form carbon and oxygen. And it goes, yo, everything's okay, man. Cool, we can move back to the main sequence. Yo, come on back, outer layers. And the outer layers like, man, dodged a bullet on that one. And the outer layers start coming back in. But that's cheating, because the main sequence, remember, is hydrogen to helium fusion in the core. We got the core part right. It is not hydrogen to helium fusion. It's helium into carbon and oxygen. So the star begins to drift away from the red giant, but it's never going to make it back to the main sequence. Sorry. Now, eventually, the helium is going to be used up in the core, and we're going to end up in the same situation we were in a few million years before. What's going to happen is now we're going to have a core that's made of carbon and oxygen. That's going to start collapsing under its own weight and heating up. We're going to actually transfer heat to a shell outside, which is now going to fuse helium in helium shell burning. The outer layers are like, oy vey, not again. And the outer layers again puff off into space, and it forms a red giant again. Now, for low mass stars like our sun, that's the end of it. There's not enough gravity to squish that carbon and oxygen to get a high enough temperature to fuse them. So in the case of the sun, that's going to be the end of the road. The second time it becomes a red giant, that's it. Hasta la vista, baby. The outer layers puff off into space, creating a planetary nebula. The core itself will eventually collapse down to form a white dwarf. But for stars that are heavier than the sun, their cores will eventually collapse enough to have enough pressure to fuse carbon and oxygen into heavier elements. And then we go through the whole cycle again, and again, and again, and again. And depending upon how massive that core is, it will be able to convert helium into carbon and oxygen into silicon, silicon into other things, etc., etc., etc. So at the end of the star's life, it looks sort of like an onion with all of these different layers. Hydrogen, helium, carbon, oxygen, silicon, magnesium, neon, blah, 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 blah. What is the end result? It turns out that if a star is massive enough, it can actually fuse the elements all the way down to iron. Iron cannot be used as a fusion fuel by anybody. It takes more energy to fuse iron than you would get back. That makes it a really crappy fuel, okay? It takes more energy to burn it than you get back. So if a star is heavy enough to actually get down all the way to iron, that is an unstable situation, boom, and the star explodes in a supernova. So our sun will never explode. Only stars that are much heavier than the sun will explode to become a supernova. There's one exception to that, which I'll get to in another video.